today. And then I'm going to kind of go a little bit quick. I've never done this group quiz stuff before. I've done different things in the past to review. Okay, so I'm a little bit leery about how long they take because I know how long they would take if you're taking them individually, but group quizzes might take longer because you're discussing more, which is what I want. So if I'm rushing today, it's because I'm trying to get a gate. I'd rather leave you more time at the end than necessary. Does that make sense? Okay. So in Unit 2, we started looking at not one variable, but two variables. Okay, and looking at relationships between two variables. So we kind of talked about if we had two categorical variables, typically that was given to us in a two-way table. And in that two-way table, what we looked for is basically, like, if you did the percentages across the two-way table, were they the same or different? Think, you guys remember doing those segmented bar graphs? If those segmented bar graphs showed differences in those proportions, that's what it would look like. We'll talk about this a whole lot in a little bit, in a couple days, but like we also, the other way of looking at that would be looking at the probability of A and the probability of A given B, and are they the same or not? Okay, so mostly in Unit 2, it was answering basic questions off of two-way tables if what we were talking about was categorical variables, okay? All right, but the bulk of Unit 2 was about scatter plots. Okay, and so let's go ahead and say I gave you this scatter plot, and I said my x-axis was time spent studying, even though this is just the lamest thing ever. Time spent studying. My y-axis is test score. And if I gave you this particular scatter plot and I said, what do you see? Describe the relationship shown in the scatter plot. I would expect you to talk about three things plus context. The three things are strength, form, and direction. As you look at this particular scatter plot, moderately strong. Form, so form is linear or not? Would you call this linear? Give or take? Okay. Direction? Positive. Great. Okay. That's the case. If I asked you to actually write out this, I would say there is a strong, positive, linear relationship between study time and test score. Do I have strength? Yes. Form? Yes. Direction? Yes. And can I tell what the labels on the axes were, right? Like, can I tell, like, the big idea behind this? Okay? All right. Now, when we talk about strength, correlation is really just talking about that strength in more depth. Okay? So,
are we not going to deal with like unusual features?
Are there any?
No, but like would it be like just a cluster of dots?
Clusters would be an unusual feature. Gaps would be an unusual feature. I don't know if you guys remember that Old Faithful set of points I gave you that had two clusters of points that you would maybe talk about. Yeah. Okay. All right. But mostly that's what it would be clusters. Or if you have like, sometimes you'll see a scatter plot where you have one really wacky point, right? And usually that would mean you have to do some sort of extra analysis, right? So for instance, what if this scatter plot had a point right here? I might say I might say that exact same statement and then say, however, there was one student who spent a long time studying and still didn't do well on the test. Right? Okay. All right. Now, so in correlation, when we talk about correlation, we're talking about R. And so some reminders about R is it's in between -1 and +1, always. R equals 0 is very weak. R equals +1 is a really strong positive relationship. R equals -1 is a really strong negative relationship. Every good?
It's 0 would it be?
If R equals 0, so some examples of like R equals 0 might be this scatter plot, right? And it turns out, now R is not your slope, but it kind of is. It's your slope, when we get there, your slope we're not really talking about lines yet, we're just talking about strength of the relationship. However, your slope is equal to R times SY over SX. You'll never be doing it by hand like that. Like, you don't need to know that. But R is the sign of the slope. Okay? But slope is really finicky because, like, things like slope depends so much on, like, units. Like, for instance, if you think about a slope of 12 inches over 1 minute, right? It could be a potential how quickly something is increasing, right? So that's 12, right? But that exact same slope would be 1 if you're measuring it in feet per minute. And it'd be 0.000 something, close to 0, if you're measuring that in miles per minute, right? So it's all of those the same relationship. So R measures strength only. It doesn't, but it turns out that when R is equal to 0, your slope would also equal 0. So, like, if you think that if your overall impression of the scatter plot is that the line would be horizontal, then yes, R is still 0. Okay? All right. R is very heavily influenced by points in the corners. So what I mean by that is if you think about this being X bar, this being Y bar, the means of my X's and Y's. If most of the points in your scatter plots are in these two corners, you're positive. So these are like the positive corners. These are the negatives. That doesn't look negative, but it is. Okay, so like when I'm looking at, say, this scatter plot, we can see, one, that this is increasing, and we have a lot more points in these corners than the other ones. Is everybody good? Okay. And the points in the middle don't affect the correlation that much one way or the other. Okay. All right. Now, a lot of the time what you're going to be asked to do is say, let's do this. Let's go back to this point, this scatter plot. All right. A lot of times what you're going to be asked to do is say, what would happen to the correlation if? Okay. So let's go ahead and say this scatter plot, including that blue dot, was there. Okay. The presence of that blue dot might make me question the strength of the relationship, right? So you might be asked, what would happen if we removed that unusual point? Would the correlation get larger or smaller? Everybody with me? So I want you to think about the correlation in that setting as the bubble. I have that bubble if I'm not including the blue point, right? And in order to include the blue point, I have that bubble. Everybody with me? Which one shows more of a linear? The red one, right? Right? So the length to width ratio of that bubble, if it changes, the correlation is getting either stronger or weaker. Okay? If it doesn't change, then removing, like, so if I had a point like this point right here and I removed that green point, doesn't change the red bubble whatsoever. Right? So removing the green point does not change my correlation. Removing the blue point would, because it would change that bubble. Is that okay?
So the closer it is to an oval, the more correlation is.
The stronger it is. One more piece of advice I would try to use when describing how the correlation would change. I do not want you to use the words increase or decrease. I want you to use stronger versus weaker. Let me tell you why. Let's say my scatter plot is this one. Everybody good? Would you call that strong? Okay. So I'm going to eyeball that and say that R might be like negative 0.85. Is everybody good? Now, what if I added this point? So I'm going from this more like this, right? Is everybody good? And so all of a sudden, my R would get closer to 0, yeah? Which would be let's say negative 0.72. Again, I'm making these up, right? Which number is bigger? Negative 0.72 or negative 0.85? So my correlation, my value of my correlation actually increased. Do you guys see what I'm saying there? But the strength of the relationship decreased. And so because negative numbers count backwards, I don't want you guys to say the correlation would get bigger or smaller. I want you to say stronger or weaker, because that helps you avoid making that kind of mistake. Is everybody okay? All right. So R also has R squared, which is the coefficient of determination. Okay. So R is the correlation coefficient, and so they're often confused for each other. Okay, the interpretation of R squared is always blank percent of the variability of whatever Y is. You're going to do it in context. Can be explained by the linear relationship with whatever X is. Everybody okay? All right. All right, so next I want to talk about equations. The LSRL stands for least squares regression line. In your guys' head, guys, it's the line of best fit. All right, if I ask you to find the line of best fit, you're always going to write it as y hat equals a plus bx. If you write it in mx plus b form, not a single thing will happen. It's fine. Okay, you guys have been drilled and drilled and drilled to do y equals mx plus b since like 7th grade. So don't think that you're going to get marked off. As long as you know what is the slope versus what is the y-intercept, it will not be a problem. The slope is always the one that's in front of the x. Is everybody good? I want to emphasize that you have to do that in context. A couple of you figured that out on the Unit 8-9 test, okay? That your line has to be written in context, all right? So let's go ahead and talk about interpreting this slope. I know we reviewed this literally right before break, just rather be, it is the change in y over the change in x, and usually you put your slope over 1, right? So what's going to happen is, first you're going to describe the change of x being 1. So for every increase of 1 blank, and that's going to be whatever your x context is, there's a predicted I'm going to emphasize that increase or decrease, depending on if your slope is positive or negative, right, of blank in y. Your y-intercept is always the point 0 y-intercept, yeah? So when anything I underline means you got to put it in context, right? Okay. When x equals 0, that's going to be in context. So what does x equaling 0 mean? So like up here is that instead of saying when x equals 0, you're going to say if somebody doesn't study at all. Spent 0 hours studying. Yeah? Y is predicted to be all right. To get the line from a regression output, you're going to use the coefficients column. Your constant is your y-intercept. Your x variable is your slope. So let's go ahead and pretend that the equation for the scatter plot I just said was that your test score is going to equal 10 times your hours plus 52. Let's, like, again, pretending, okay? If I then asked you, okay, someone studied for 1.5 hours, can we turn that into what is their predicted test score? What would you do? You would plug 1.5 in for the hours. And you get 67. Is everybody good? Everybody good in terms of using the line to make predictions? All right, so now let's go ahead and say that Bill studied 1.5 hours and got a 73. How did the line do? The line underestimated, right? Is everybody good? Okay, and if I asked by how much, you would say 6. Yeah? Okay, so a residual, to calculate the residual, you take actual minus predicted. And all it is the error for that individual point. A plot of the residuals. So you would expect some points to be above the line, some points to be below the line, yeah? Okay? A plot of the residuals, if the line is a good line, should show no pattern. Okay? If the model is appropriate, no pattern on the residual plot because you would expect them to be equally scattered around that equation. Everybody good? In terms of over-predicted and under-predicted, don't overthink it, okay? Because a lot of people would say, look at this is a positive residual, that means over. Okay? Is everybody with me? All you have to, you can just compare the two numbers to say 793 is bigger than what the prediction is, right? What actual was bigger is under-predicting. Everybody good? Okay, and in the end, instead of saying the over-predicted or under-predicted, you can say the model was 6 units lower than what actually happened. Okay? All right. This is just going through some slightly different things here. This is on your formula sheet. I don't want you to stress about it completely. I could ask you to find the slope by hand by giving you summary statistics. Okay, so this is the body weight of hikers along with the weight of their backpacks. So you would think people who are heavier need to carry more food, need to carry heavier clothes. Their hiking backpack would be heavier. Okay, so all right. So in this case, you have so your body weight is X, your backpack weight. So this would be my X. This would be my X Y. This would be X bar. This would be Y bar. Okay, so and then we have here what the R is. Okay, so if I wanted to find the slope would be 0.794 times 3.46 over 30.3. To find the y-intercept, you would say, you'd basically put in x bar and y bar into that y equals ax plus b and fill in everything we know. So y bar would be 28.63 equals, we have our slope of 0.0907 times x bar plus my y-intercept. And then if I asked you for the equation, you would say backpack hat equals 0.0907 times body plus 116.3. That's probably the least likely way you'd be asked to come up with a line of fit. The most likely way you'd be asked to come up with a line of fit would be using one of these tables. okay? So, like I said, you use the coefficient column. All right, so this is heart rate versus running pace. I think this might even be an example that was in your notes, okay? Is everybody good? All right, so as I look at this, if I want to come up with that line, I'm told the dependent variable is BPM, so I'm doing BPM hat equals negative 10.53 times the pace plus 255.6. Slope-wise, we would say for every increase in 1 minute per mile, because pace would have been measured in minutes per mile, so that's every increase of 1x, there's a predicted decrease of 10.53 beats per minute. When you're doing R squared, you're always going to have two R squareds in these tables, and you're always going to ignore the adjusted one. Okay? So in this particular case, interpreting that R squared, I would say 85.6% of the variability in heart rate, or BPM, okay, is explained by the linear relationship with pace. All right. You guys, if I know R squared, how can I find R? Take the square root. Okay, I agree. However, so R is going to equal the square root of R squared. But we want to make sure we're taking the square root of the decimal version of R squared. Okay? And we have to be really, really careful. Because it could be positive or negative. It is not both. But it could be positive or negative. And the way I make that decision is the slope of my line will tell me whether or not overall this is positive or negative. Okay? So in this case, that correlation would be negative. Are we good? All right. Now, use this line to predict the heart rate at 8.5 minutes per mile. What would you do? Negative 10.53 times 8.5 plus 255.6.
What would the y hat be? Would we have to put a y hat or just that?
I mean, y hat, the hat is basically the predicted y value. So BPM hat would be predicted for that particular x.
Okay.
So my residual would then be 158 158 minus 166.095. Bless you. Which would be negative 8.095. So did the model over-predict or under-predict? In this case, the model over-predicted. I know that because my prediction is bigger than what actually happened.
I thought it was actual minus predicted.
It is. The actual would be the 158.
All right.
This is the predicted. So my interpretation, the model over-predicted by 8.095 beats per minute. All right, let's take this time.